Okay, so I'm recording this session and then I'll upload it on YouTube if Cat Courses doesn't let me. It'll just be on my channel, so you guys can go check it out. Okay, and I already uploaded the annotated discussion for you guys. So all my notes that you're seeing. That's too small. So yeah, you can follow along with me. Remember that I highly recommend that you have a PDF editing software. I'm using Drawboard PDF, but you can use just about anything. You can YouTube it, like what are the best PDF editing softwares for students, and then you'll get like a lot of free versions. I paid $7 or $8 for mine, and I've had it for about 10 years. They don't charge you every year. It's just like a one-time fee. So for me, it was absolutely worth it. I have 45 documents open right now. And so it's pretty cool that you can just like rotate between documents and then just annotate them as you go. So here, I would recommend for your next test, I hope that now after your first test, you realize how important it is to have your terminology down. And you can't be like, I think this is that. You have to know like for certain what things are. So what I recommend for you guys is to go ahead and annotate right here, like for yourselves, like what all of these are. Like she put them here for a reason. So the delta G, for example, is, what is it? Free energy change. And then I uploaded last week my the first lecture annotated. And I have a beautiful slide there about that has everything for like endergonic, exergonic, and it's like 10 different topics all on one slide. You should memorize that slide because it'll help you through the final. So I just added it last week to my folder that I have on Cat Courses for you guys. Okay, so go check it out. So yeah, you have to know what all these are. And then the first thing we're going to start with is this energy diagram. So remember that when things have a negative delta G, that means that the reaction will happen spontaneously. If the delta G is positive, then the reaction will not happen because you need to add energy to make it happen. So when things have a negative delta G, they will happen spontaneously, but it does not mean that they will happen quickly. A lot of students lose points on exams because they assume that a negative delta G, even if you have a really high negative delta G, they assume, oh, it's going to happen super fast. No, the reaction can take 1 second, or the reaction can take 1 million years. And it's still considered spontaneously because it has a negative delta G. So it's important for you to have all this just like down. So for this energy diagram on the y-axis, we have energy. So I always like to label high energy on top because they didn't give me any numbers. So just to help myself out, high energy on top, low energy on the bottom. On the x-axis, we have reaction coordinate. And then right here, we have a curve that they just give you, and you're responsible for labeling this entire curve. So practice drawing it a few times and that should be fine because it's pretty simple. So over here we have a substrate, over here we have a product. This is delta G, and then below this line is standard delta G, and then up here is transition state. And I'm going to draw some stuff on the board that's going to help you understand all that stuff with pictures and stuff. Okay, so I'm going to start off with this reaction. So try to color code everything that you do because it's going to help you memorize things better. All right, so let's see, we're going to go ahead and start with enzyme plus substrate and then this is a reaction rate forward and then a reaction rate backwards. And that equals enzyme plus the substrate in a complex form because they're together. And then you have another reaction, a reaction rate moving forward and a reaction rate that can move backwards. And here you have an enzyme plus product. So to me, that doesn't really tell me much. So I absolutely have to have little drawings to know what is happening. So we're going to go ahead and draw our enzyme. And let's say that we have an enzyme. And the function of this enzyme is that it takes in a substrate, which is a circle. And then it turns that circle into a triangle. So this would be the reactant, or actually this would be the substrate. And this would be your product. Okay, so here you only have the enzyme by itself. And then you add it to the substrate, which is our little circle. And that'll give you an enzyme substrate complex. So that's the enzyme with the substrate stuck together. That's why it's a complex. And then that turns into the enzyme by himself. And he let go of the product, which was a triangle. So on that graph, oh, sorry, let me finish this. All right, so these guys are reaction rates. So you have K1, that's the reaction rate, like how long does it take to go from having individual enzyme and substrate to a complex. That's your rate. And then K minus 1, all that is the backwards reaction. You already have the enzyme substrate complex, and then you separate them again. That's all that is. And then over here we have K2. So that's how long does it take to get from enzyme substrate to enzyme product? How long does it take this enzyme to convert the circle into a triangle? And remember, rate is like velocity. Like how fast does this happen? And then again, K minus 2 is just the backwards reaction. Okay. So now we can talk more. Now we can talk more about, we have one question. Thank you. Okay. So now we can talk more about what we're seeing up here. So this is all that this is saying. The substrate is what you start off with, so our little circle. And then up here you have the transition state. And that's when you're turning that circle into a triangle. And that transition state has a lot of energy. So you can look at the energy diagram on the y-axis. So it has a lot of energy. And then you go down, and then at the very end, you have your product. So that's the triangle, right? Everything makes sense? Pretty simple? Okay. So now here we have our first question. If you were to add an enzyme to this reaction, which one of the following changes would you expect? Okay. So they give you these things in like kind of different, it's like a backwards way of looking at them. So I'm going to go over all of them. So they give you an enzyme. What are the benefits of having an enzyme? So add enzyme. And what are the benefits? So the first benefit is an increased K1. So to me, this doesn't say much because we barely learned like these terms and stuff. So I like to put in parentheses a simple explanation for myself. For when I go over this later, like if I want to review all my worksheets right before the exam, wouldn't it be so nice if all the information was just on one document? So yeah, simplify it for yourself. What does this increased K1 mean? So it just increases the rate at which enzyme and substrate get together and form the complex. Right? So if you add an enzyme, that makes sense. You're going to increase the rate. Does anybody remember what the function of an enzyme is? So increase reaction rates by decreasing the activation energy. Okay, so this just means increase reaction rate from enzyme plus substrate to enzyme substrate complex. Yeah, makes sense? Simple enough? Okay. Okay, 2 is decrease delta G. Please make sure to sign the attendance. Okay, so decrease delta G. Well, does that make sense? What is delta G again? So if you add an enzyme, does that decrease delta G? So when delta G is negative, so I like to just rewrite this for my own sake. When delta G equals negative, and I want to emphasize negative. When delta G is negative, reactions equals energetically favorable. They happen spontaneously. The more negative the better. So decreasing delta G means that it will be more negative. Your delta G will be more negative, and that's great. You added an enzyme, it reduced the activation energy that you require to make that reaction happen, and so the delta G is negative, more negative. And then the third one is increased K2. So that makes sense that if you add an enzyme, it's going to increase the reaction rates. Like we have 2 reactions here. So the first one where you add the enzyme plus the substrate to make the enzyme substrate complex. And then the next reaction where now you already have the enzyme substrate complex and you're just waiting for the enzyme to turn that circle into a triangle. So you would have your enzyme, and then once it turns it into a triangle, it releases it. So it can capture another circle. Enzymes are really hardworking. They like never want to stop. So they immediately release their product and go grab a new substrate, turn it into a triangle, and then release it. So that makes sense. So second, so increase rate of second reaction. All right, so after you guys write your definitions for all that stuff, like once you fill this guy in, everything will make more sense for you. Okay, so sometimes the difference in standard free energy content, that's delta G, between a substrate and a product is very large. So they're saying the delta G is very negative. So we know that that's great. But the rate of chemical conversion from substrate to product is quite slow. Why? So the reason is because the rate of a reaction, and this is something you have to like memorize, I would say, the rate of a reaction does not depend on how negative your delta G is. The rate of a reaction does not depend on how negative your delta G is. So we talked about it earlier, the rate of your reaction depends on the activation energy. And so the example that I gave my other class is like, let's say that I want to go to Disneyland and the activation energy would be the cost of the ticket. So if it cost $1 million, how many people can actually afford to go to Disneyland? Not that many, right? Especially if you have like a whole family. Not that many. So I would consider that the reaction rate would be slow. But if the activation energy is low, so if the cost of a Disneyland ticket is only $20, how many people are going to be able to go? A lot, right? So everyone's just going to crowd in. And then I consider that like, yeah. Does that kind of make sense a little bit? Yeah. Okay, so we got number 2. Number 3, for the simplified representation of enzyme catalyzed reaction shown below, the statement ES is in steady state. Okay, so I wrote some notes for you. We're going to go over those first, and then I'll explain it on the board. So there are 2 reactions happening here. That's reaction 1. So wherever you see the little reaction arrows, this is reaction 1, and then this is reaction 2. Okay, so they each have their own rate and the definition of steady state, because this question is asking you about steady state. When the enzyme substrate complex is constant, the formation of enzyme substrate is equal to the loss of enzyme substrate. So when you're talking about steady state, this guy right here is the star of the show. So he is right in the middle of both reactions. Okay, so steady state. We have the enzyme substrate complex. It has to remain steady. So if you make 100 on this side, you have to break down 100 on this side because it has to remain steady. The enzyme substrate complex has to remain steady. I'd recommend watching a video on this because it's kind of hard to explain unless like we go through, I don't know, like a 10-minute thing, but you have more problems. So I'd recommend there are a lot of good videos on YouTube. But let's go over the answer. I'll write it right here. So the answer is D, and it's K1 enzyme substrate is equal to K minus 1 enzyme substrate complex plus K2 enzyme substrate complex. So the way that this works, the way that I think of it, is kind of like cross multiplying to cancel out. So here you have K1 positive, so you need the other reaction to be negative. And here you have K1 negative, so you need the opposite reaction to be positive. So that's why so here it's K minus 1. K minus 1 of the enzyme substrate complex is equal to or plus K2, which is on the opposite side of the enzyme substrate complex. So I don't really know how else to explain it. But it's kind of like you have two reactions and they have to cancel out in order to keep that enzyme substrate complex the exact same. If they don't cancel out, then you're either going to lose some of that. And if they don't cancel out, you can also gain some of it. I guess canceling out is a good way to put it. Okay, so now we are talking about this graph, and this is really similar to the graphs that we talked about last week. So that's really cool. But last week, the ligand was the star of the show. This time it's the substrate concentration. So remember on the x-axis, we used to have the ligand concentration in micromolars. Now we have substrate concentration in micromolars. And then on the y-axis, we used to have y, which was the percent of binding sites occupied. So this time we just have velocity. So it's micromolar per second. And what we're looking at is Michaelis-Menten kinetics. And that's just talking about enzymes, like how good are you? Like, can you turn 100 circles into triangles per second? Then you're pretty good. Can you turn only one circle into a triangle per second? Then you kind of suck, right? So that's all that Michaelis-Menten kinetics is looking at. So if you break it down, it's pretty easy. They will usually give you a curve. And so we have this curve here. And then there's a few, we're going to get into the terminology. So remember, x-axis is substrate concentration, y-axis is velocity, and now we're looking at maximum velocity. That's just, you draw a line at like your highest point, and that's your maximum velocity. So to me, it looks like 80. Looks like the maximum velocity is 80. But on the answer key, it says 90. So I'm not really sure why. If somebody shoots me an email tonight, I can remember, because there's a lot on my plate right now, so I can remember to email the professor and be like, hey, is this a typo? Like, what's happening? But most likely it's a typo because the maximum looks to be about 80. And then if we go to 50% of 80, it's actually 40, but on the key, it has this, on the key, it has the, it has it at 50. So let me see if I can just erase that. Let me delete it. Okay, it's not letting me. Do I have an eraser? Yeah, right here. Okay. Okay, so for me, I think it's more like, let's delete this one too. But yeah, this is supposed to be very simple. So half of the maximum velocity, you guys remember last week, half of that was a really important number, and this is the same thing. So half of the maximum velocity is 40, because we said maximum is like 80. And so wherever that blue line crosses that 40, you're going to go straight down right? We remember this from last week, is really easy. And guess what? That's our Km value. That's your Michaelis-Menten constant. So terminology. X-axis is substrate concentration, usually in micromolar, sometimes in nanomolar. And then on the y-axis, we have velocity in either micromolar per second or nanomolar per second. And then they will give us a line, and then they will tell you, find the maximum velocity. Super easy, just bam, right there. 80 micromolar per second. What's half of the maximum velocity? 40 micromolar per second. You draw your line, and wherever the line that they gave you, that blue one, wherever it intersects with that half, that 50% line, which is 40, you just go straight down, and that is your Km. That is your Michaelis-Menten constant. The lower, so remember, big picture here. What we care about is enzyme kinetics. How good is this enzyme? What is the efficiency of the enzyme? So the lower the Km, the better the enzyme is working when substrate concentrations are small. Use a Km to determine the enzyme's catalytic efficiency. So if it takes an enzyme 10 micromolars to get half of the maximum velocity, that enzyme sucks. Its efficiency, its catalytic efficiency is low. But if an enzyme only requires 1 micromolar to reach half of the maximum velocity, that enzyme's catalytic efficiency is very good. It's very high. So this guy who requires 10 micromolars, he's the one who can only do like 1 circle and turn it into a triangle per second. Whereas this guy over here that only requires 1, he can do 100 per second. So that's the big picture. Once you have your terminology memorized, everything will be easier and you'll be able to solve problems. And I think by now we also know kind of like how important it is to know your formulas. And you don't have to have them memorized, but you should know what every single letter represents. So V naught, that's the initial velocity, and usually it's usually half of the maximum velocity. That would be like your V naught right here. So your V naught is equal to V max. That's half your maximum, your maximum velocity, times the substrate concentration divided by your Michaelis-Menten constant plus the substrate concentration. So that's one of your formulas. The other one is Kcat is equal to the Vmax divided by the enzyme concentration total. Now, when I was an undergrad, I just could not, I missed the whole like T. And then for one problem, I spent like 3 hours on it because I couldn't understand like what the T was. And I would like work it out and I just kept getting the wrong answer. Enzyme T, that means total enzyme concentration. So this little guy, this enzyme, he's free. He's not attached to anything. He's free. So we need to include that concentration. And then this enzyme is attached to the substrate. We need to include that enzyme. So the ET, enzyme concentration total, they're talking about all the enzyme, because sometimes they'll give you a problem. It'll be like a whole paragraph and they'll tell you, oh, you have this much free enzyme and then you have this much substrate. So they're not telling you, you need to add those two. You need to know that for your formula, okay? So Kcat, this is the enzyme's turnover number, the amount of substrates that can be converted into products per second. This is the catalytic efficiency. So I noticed in like your lecture PowerPoints and also in like the discussion worksheet, they use different terms. So I try to catch all the different terms and put them all in one location for you. If you find more terms, go ahead and just add them for yourself, okay? So again, catalytic efficiency, turnover number. On the exam, they can use any of those terms. And you have to just know that that's Kcat. Okay. All right. Okay, and then here's the pattern that we see. Catalytic efficiency is equal to Kcat divided by Km. So that's like another formula that you got to know. Like if they tell you the Kcat and the Km and they ask you for catalytic efficiency, if you only learn these two formulas, you're going to be like, they didn't give me enough information. How am I supposed to answer this? Well, this is another way to do it, and they expect you to know it. Again, flashcards, or for me, what helps is a dry erase board. It helps me more because I have to physically write things down until I no longer need my notes. And then at that point, they'll be in my brain. So whatever works for you. Catalytic, yep. Kcat is the enzyme's turnover number, and it's also called the catalytic efficiency. So again, catalytic efficiency is equal to Kcat divided by your Km. And the higher your Kcat, the higher the catalytic efficiency, the lower the Km. And that makes sense because we talked about how the lower your Km, that's the more to the left that you are, the higher your efficiency, because that enzyme only requires a tiny little bit to reach half of the maximum velocity. So lower Km equals higher Kcat / catalytic activity. So that's your pattern you got to have memorized. And then sometimes they'll throw in like another enzyme, and they'll be like, which one has a higher Kcat or which one has a higher Km. So you have to know all this stuff back and forth. So let's go ahead and look. Estimate the Vmax and the Km from this graph. So Vmax we said was 80 microns per second. Km, that was a half the maximum velocity all the way down. So our Km was 1 micromolar. Calculate the Kcat knowing that the enzyme concentration is 0.05. So here they're giving us the enzyme concentration, and they want us to figure out the Kcat. So let's go find our formula that we got to use. So they gave us the enzyme concentration. They want the Kcat. So all we need is Vmax. So you just got to put in the Vmax. You see how it helps when you know your formulas? Because it's really easy to know what to plug in. So for them, they said 90. So it would be 90 divided by the total enzyme concentration, which they said was 0.05. So it's just 90 divided by 0.05, and it equals 1800 per second. So the S with a negative sign up top, it means per second. So 1800 substrates per second are turned into products. So 1800 with this enzyme, 1800 circles are turned into triangles in 1 second. So its Kcat / catalytic efficiency / turnover number is really high. So it's a great enzyme, really good employee, right? Yeah. Okay. Calculate the value for Kcat divided by Km. So they gave us a Kcat, which was 1.8 times 10 to the third per second, divided by Km, which was 1 micromolar, and they said 10 to the negative 6 in units of molarity per second. So basically, they wanted you to write it in scientific notation. So you have to be able to write it in like decimal format, in this whole micro format, and then in scientific notation. So remember, micro is 10 to the negative 6. So just practice that if you haven't practiced it in a while, but it's really easy. In the same graph, draw a curve for the data you would expect for a second enzyme if the Vmax for both enzymes is the same, but the Km for enzyme 2 is 3 micromolar. So they're saying draw another line for another enzyme, but this time the Km is 3 micromolar for that enzyme. So I drew it out here, and they said the Vmax is the same. So I kept it at 80. and you always have to start from the beginning. And then they said the km for this guy is 3 micromolar. And if we remember, the way that we got km is that we went ahead and drew the line where they intersect. Well, I was a little bit off here, but yeah, we drew it here. And that's your km. So it's really easy when they ask you for km because it's like, oh, that's so easy. It's just right there. Let me draw it in purple. Okay, so remember, you start here. And so I like to draw my km line first. They said 3 micromolar, so bam, it's right there. And then you just go straight to there, right? And then you just keep going up. And that's how you would do this on a test or a quiz or whatever. Easy, right? So the Vmax is the same, km is 3 micromolar, and now they're probably gonna ask us questions. Oh yeah, who has a better efficiency? The lower km has a better efficiency, a better catalytic efficiency, a better turnover number, and it has a lower km. So for this question, I gave you guys a lot of notes and it was pretty simple, so I think you can do it. I want to go over which question. Oh, yes. Okay. This concept. So this we learned Michaelis-Menten, right? So now equally important to Michaelis-Menten is this guy. It's called a Lineweaver-Burke plot. I highly recommend that you watch a YouTube video on each of those and take good notes. Practice drawing these because they're so important. So I'm going to draw your Lineweaver over here, and all I'm going to do is label the axes. So my last class, they loved it, and I feel like they understood it. Like they felt more comfortable with the material. They weren't so scared because this stuff is scary. Okay. So what is a Lineweaver-Burke plot? So what was the purpose of it? I wrote it down for you guys. I don't know. I gave you so many notes here, so definitely check this out. Thank you. Okay, so the Lineweaver-Burke plot was to get a better estimate of your enzyme's activity, because anytime you curve something, it's a little bit more complicated. And they said, okay, we want to deal with only straight lines because those are easier to just visually tell what is happening. So that's what they did here. So here is our line. And then for the one of the first times, we're going to have negatives and stuff. So this is Lineweaver. And all they did is they took the inverses of the Michaelis-Menten stuff. Inverses, okay? So we have 0.5 and we have 1. And then we've got negative 0.5 and then we have negative 1. And the x-axis is equal to 1 over the substrate concentration. So x-axis equals 1 divided by the substrate concentration. So like I said, the inverse. And we already talked about substrate concentration, so x-axis easy, right? Okay, y-axis is 1 over the V0. That's the initial velocity. So this is y-axis. So easy, right? Because we know what all this is. Okay, so here we have 1, 2, 3, 4, 5. Okay, and here on the left, they gave us some data. They said the substrate concentration is all this. The product formed is all this. And then they give you more substrate. So really they should have given you like one long, because it's really 6 substrate concentrations and 6 products. The fact that they put it like this threw me off because I'm like, are those supposed to be different columns? They're not. The ones on the right just go underneath the ones on the left. So the first thing you have to do, you have a question? No? Oh. So the first thing you have to do as a student is get the inverses. So I like to throw in an extra column, and so it's down here for you. So they have your V naught, they started with V naught, but just make your columns. So we have all the V naughts, which was the product form. They don't tell you that that's V naught, that's the V naught. So I went ahead and wrote it for you in blue. So you have to make the column. So you have V naught, and then you have 1 divided by V naught. And that gives you this, your x-axis. And then you have your substrate concentration column, all 6 right here. And then they tell you, and then you make your new column 1 divided by substrate concentration. And it's that easy. You just go 1 divided by 1.5, and that equals 0.67. 1 divided by 2 is equal to 0.5. 1 divided by 3 is equal to 0.33. You guys got it? Easy. So step 1, make your columns. Then all you do is graph. So I went ahead and wrote in red for you, x-axis, y-axis. So that's what you're graphing. So it's actually pretty easy if you know your terminology, if you know your axes, if you know like the whole picture, the whole concept of what is happening, then it's really easy. All you do is graph now. So my x was 0.67 and y is 4.8. So x is 0.67, like right here, and then 4.8, so like right here. Okay, and then the next one is 0.5 and then 4.2. So 0.5 and then 4.2 right here. And then the next one is 0.3 and then 3. So 0.3 and then 3. Okay, so this is just going to be a straight line. And then mine's not straight, but that's going to be a straight line. So what happens is we are looking for 2 points. So the line Weaver Burke plot, we are looking for 2 points. We just did all that, which was easy steps. It's just that there's a lot, so pay attention. And we're looking for 2 things. We are looking for whatever crosses the y-axis, and we're looking for whatever crosses the x-axis. Whatever crosses your x-axis, that's your 1 over km. That's your 1 over V max. So you can get a problem where they make you do all this stuff, take you like 5-10 minutes to calculate everything out, get your points, draw your line, and then you get your 1 over km, 1 over V max. They didn't ask for your 1 over km. They didn't ask for the inverse. For your question, they might ask you for just the km. So how do you do that math? It's so simple. Okay, I actually love it. So all you do, let's say that this is like, let's make it an easy number. Let's say it's 2, like 0.2. So you would just do like 1. You would say 1 over km is equal to, let's say your number was like 2. So all you do is use your algebra or math rules, right? So you're allowed to just swap those 2. So you would do 1 over 2 is equal to km. And that's it, that's your km. And you do the same thing for Vmax. So pay really close attention to what they're asking you. Do they want you to find the x-intercept, the y-intercept? Or are they asking specifically for VKM value and the Vmax value? Okay, does it make sense? Not too bad? Because this is one of the toughest things that students lose points on. I never understood this as an undergrad. I graduated and never understood this. So I hope you guys do. And then that's all I have for you today. We've got 4 minutes left. Does anyone have any questions? If you don't, I'll take the roll call. Here you go. Okay, I'm gonna go ahead and stop recording.